Chapter 10, everybody. This is a good time to remind ourselves that we've seen a reaction with water before, and it was the acid catalyzed hydration of alkene. So just a reminder, and you're not writing any of this down, we had this reaction and something like that and something like that, and we're supposed to give this reaction here. Yeah, this is hydration, right? One of our first mechanisms. What's the first step in this mechanism? Protonation of the alkene with a strong acid like sulfuric acid or toluene sulfonic acid, pictured here. Not copying anything down yet. In this one, we only need one carbocation because there's only one product listed. We're going fast because it's review. You get an oxonium ion here. We're going to neutralize our oxonium ion very shortly. What is going to be used to neutralize the oxonium ion? It is the conjugate base of our catalyst. Yes, and I heard several people saying OTS negative. They were correct. And that's going to grab the H and finish off our. And I do expect everybody to be able to fill in this blank. What is the opposite of a hydration reaction? Dehydration is going to be our next topic, and it will be new. You will be copying this out, starting with the word dehydration of alcohol. You're going to do name. And we're going to start with the product here. So everything starts here in this red box to the left, starting with an alcohol. Treating it with the same catalyst, could be hots or sulfuric acid. And this hots needs some more hots. That hots. What's that hot? Heat. Why would we need heat? Because this reaction is what kind of reaction in terms of heat? Generating a less stable pi bond. What do we call that kind of reaction that generates a less stable molecule? Endothermic. Yes. We're going to require a lot of heat. Okay. The thing about the mechanism in chapter 10, this is chapter 10, a little reminder. One of the reactions is called dehydration of alcohol, chapter 10. And a principal theme to make alcohols react is first, you must make them into better leaving groups. Hydroxide is not a good leaving group at all. Hydroxide is the conjugate base of water with a pKa of 16, meaning hydroxide is terribly unstable. Please don't have hydroxide leave. One of the easiest ways to make hydroxide the better leaving group is to protonate it. That's what we do first. We have a strong acid, we have an alcohol functional group. Protonate it first. It is now a good leaving group. You're copying everything inside this red box as activity 1. Just what's inside this box to the left of the screen. OH2 plus is a better leaving group. And you have OTS negative for future use. Yes, it's acid catalyzed. Acid catalyzed, just like the forward reaction before of hydration, this one, acid catalyzed. Same catalyst for the backwards. Now you have two choices for this secondary RX. Oh, please don't tell me that you can't see that's an RX. What does X stand for? Like our whole last week? Leaving group. I couldn't call this a secondary RX originally because it didn't have a leaving group on it. Hydroxide is not a good leaving group. Do not call a molecule with hydroxide any kind of RX. It doesn't have a leaving group. Now, this is the conjugate base. If it leaves as water, the conjugate base of water. Okay? So it's leaving as water. It's the conjugate base of hydronium. That's what I'm saying when it leaves as water. When answering the question, is it a good leaving group? Here, it's left. That leaving group is the conjugate base of which acid? OH2 is H2O, by the way, is the conjugate base of which acid? H3O plus. pKa negative 2 means what I just drew, H2O, is an excellent leaving group. Your choice for this is E2 or E1, and I know we had a bunch of rules and what do we call them? We call them overrides for Chapter 9. This is not about overrides in Chapter 10. Forget you know anything of elimination from Chapter 9. Forget it. This is a whole new ballgame. Alcohol chapter, you got to first make the thing into a good leaving group. That's totally different than Chapter 9. The leaving groups were already there. All bets are off now. This thing can either make a cation to do an E1 if the cation is stable. Or if it's not a stable cation, a carbocation, you got to do an E2. That's a secondary carbon. What are your comments about the stability of the cation? You got here's your three choices. It's a wonderful cation when it's secondary. Choice 2, it's a lousy cation, I can't make it. Or choice 3, Mobatif. Thank you. It's a Mobatif cation. Okay, so when it's Mobatif and you don't have any other decision-making things, go with the cation. Just go with the cation. Secondary, cations are pretty good. They're not great. They're pretty good. So we're going to do secondary here. Our next example will be primary, where you're not allowed a cation. Okay? So you'll know how to do both after we're finished the next one. So this, we're going to go with the E1. E1 because C plus is OK. OK is defined as secondary or better. Got it? Secondary or better. So there's your mechanism, and here's your cation. If you don't have an OK C plus, you're going to do E2. That will be our next example on this same video. So how do you get that to be the alkene pictured above? You're almost done. In fact, I should make this blue, because that H needs to go. Yes, the conjugate base of your catalyst becomes the catalyst again. There's a meow action going here. And it's the same E1 mechanism as Chapter 9. Make cation first, eliminate it second. When you grab the H, it's called elimination. And that gives you your product. So acid catalyzed dehydration. It's our first hour today. Dehydration will be our next. Oh, we did dehydration. We're doing it, sorry. Condensation will be our next topic, but I'm looking way too far ahead. So that one needed quite a bit of heat. This next one, also in the same box, needs quite a bit more heat. Here's a primary alcohol. You are not allowed to make a carbocation from that. You're not allowed to make primary carbocations from anything anymore. We know that. We learned it. Hots or sulfuric acid, I'll stick with hots for the day. This one needs about twice as much heat. I hope that's clear. First step is exactly the same. Protonate. Make it a good leaving group. Get used to answering that question. Why did you protonate the alcohol? Always the same answer. Make it a better leaving group. You got an oxonium. One, two, three, four, five. 1, 2, 3, 4, 5. Good. And the position with the leaving group has a Greek letter, right? The carbon with the leaving group is called which Greek letter? Alpha has the leaving group. What does beta have to have for elimination to happen? An H. It has 2. It's E2 time. You need the base that you just made. You're not allowed to make a primary carbocation. So when I said E1 because C plus is okay upstairs, it is not okay when it's primary. You cannot do the E1 mechanism. You're going to do the, which other one? E1's not possible. You got to do an elimination to make pi. Which one are you using? There's an E1, there's an E2. And the base grabs the beta H simultaneously while the pi is happening, and the leaving group is leaving E2. So that is your story for dehydration of alcohols. In a nutshell, E1, E2, you're going to put your name on it, and come get it very soon. Make it a little smaller, right there. Everything below the red line, okay? Everything in the red box. Oh, sorry. 241, getting out of your way shortly. Ending video. I should have done that a while ago.